Hi everyone, it's Nil. As promised, I will be posting some CodeExpert videos to help you prepare better for your exam. The first one is a graph question called Graph Sets. You can find it under Test Exam 2021 Winter 2 in CodeExpert. So let's start. Let's start by reading the question. On the left, we have our question, and on the right, we have a blank space to show you what I would normally write down in an actual exam situation. So it's good to write little notes to the side on the paper that we will be providing, just so you have your intuition and you note the right things and focus on the right things. So let's start. You are given an undirected connected graph with n nodes numbered from 0 to n-1 and m edges between them. So I will write down undirected connected n nodes from 0 to n-1, m edges then. The nodes of the graph are partitioned into sets. Okay, we have sets in the following way. Node 0 forms a set of its own. Okay, this sounds like a base case to watch out for. Suppose that node 0 is removed from the graph, then the nodes in each connected subgraph of the resulting graph forms another set. Okay. So thank God we have an example below in which the nodes are colored according to the set they are in. Specifically, the sets in this example are 0, 1, 2, 3, 5, 6, 4, 7. Okay, so we need to understand this like the following. So node 0 is a set of its own. Okay. And if we remove node 0, removing a node means we remove that node and every edge that contains the node. So we would, in this example, we would remove 0 and then this, and this edge. So the resulting graph would look like this. Wait, let me. Okay. So you can see why each of them is a different set, because here we have a connected component, here another one, here another one. So in total, for example, this could be like, if node 0 is set 0, this could be set 1, this could be set 2, and this could be set 3. Okay, now it's looking plausible. Then, what are the questions? Given such a graph, you have to answer queries of the following type. First one, hasCycle. Okay. So let's see if it's an easy one. Okay, so in graphs questions, you can look at the points that each sub-question has and just estimate how hard that question is. So here we have hasCycle is 4 points, hasCycleWithoutNodeZero is 4 points, so they are like relatively easy. isSameSet is 8 points and getShortestPath is 8 points again. So from this I understand hasCycle and hasCycleWithoutNodeZero are relatively easier ones, so where we have to output just a number, where we do some short calculations and so on. However, the ones in pink, isSameSet and getShortestPath, tend to have some more difficulty. we could be using DFS or BFS on those ones, or another algorithm, maybe Dijkstra even. So we need to keep that in mind. This is a good clue for that. It doesn't have to hold all the time, but 90% of the time it goes. So, okay, let's move on. Wait, let me just color accordingly. Okay. hasCycle. Return 1 if the graph has a cycle and 0 otherwise. Okay. And second question, hasCycle without node 0. Suppose that node 0 is removed from the graph. Return 1 if the resulting graph has a cycle and 0 otherwise. Alright, this is also relatively easy. Third one is SameSet. Given two nodes x and y, return 1 if they're in the same set and 0 otherwise. Alright. Sounds like DFS because remember, DFS, we use DFS if we're talking about connectivity. So connected components, if it's reachable or not, and so on. In those kind of questions, we use DFS. Alright, so this sounds like a DFS type of question. And next one, getShortestPath. Wait, this just irritates me. Let me just quickly correct it, sorry. Given two nodes x and y that are in different sets, return the shortest path distance between them. Alright, so this is a typical BFS question. Remember, we use BFS if it's about distance. Alright, so you can see why I chose specifically this question, so that I will be able to show you DFS and BFS implementation and how I do it. Alright, so let's move on. You have to implement the 4 methods described above. In addition, we provide an initialize method. Okay, this is something new, which we guarantee to run before any of the queries. Okay, feel free to use this method, for example, to initialize information that you want available in all of the queries. Of course, the time consumed by initialize counts towards the time limit of the problem. Alright, so we will see what this is in the code template, but from this, what I understand is that we can actually for example, do the BFS here once and just mark the distances and use them in every query. And we can definitely do that. It sounds like a weird thing, but it's really not that hard. So let's continue. For an easier implementation of the queries, recall and make use of the fact that the graph is connected. So this is a hint. So to say that we will use that our graph is connected, as we noted above as well, here. So, grading, as I said, the points are a clue for the difficulty of the question, and also the runtimes of each query will be a clue. Not specifically in this case, but in general it may be. So, and O of n plus m time implementation gets 4 points. And O of n plus m time implementation gets 4 points, and O of n plus m plus q time implementation gets 8 points. So this will happen if we have that method inside the initialize method. Like if we have that subroutine inside the initialize method, but otherwise we would have the DFS multiplied by the query number, so we would get the other runtime, which will cause us to get only half the point. So watch out for these kind of things. And getShortestPath is also the same. And attention, you are not allowed to use imports explicitly or implicitly other than the method imports already in the code template. Alright, you see the percentage of your submission in the CodeExpert system instead of points. Alright. So, let's quickly check the code template first and come back here to, write down our ideas about each question. So our code template looks like this. This is just for me to be able to write notes above them, but it's basically just the CodeExpert copied here, so it starts from here, then goes on like this, and goes on like this, and this is the end. So, all right, at the top of our code template, we see a main function. Then they read the tests, the test cases, they create the graph, they call the initialize function as promised, and then they read each type of query and they print out the answer. So you don't worry, you don't need to understand all this. But it's also good to understand once to give you a general idea of how they test your solutions. What you need to definitely understand is how the graph is initialized and the comments here. But I will run you through the main function as well, just so you know what happens where. So, first things first, uncomment the following two lines if you want to read from a file. Also make sure the lines I commented when testing with the test button or when submitting, otherwise your code may exceed the time limit. Okay, watch out for this. If you uncomment those lines to just test for some cases, which you can do obviously, don't forget to, uncomment them. Otherwise, you may have issues with your time limit even though your solution is absolutely correct. So watch out for this. Next thing, this main function first reads an integer number, which gives the number of the tests in the following. And then for those number of the tests, it first reads three numbers, number of nodes, n, number of edges, m, number of queries. Then it initializes an edge array of edges with number m and 2 for the edge starts from vertex A and goes to vertex B, or it goes to both sides in this case because it's undirected. So for I starting from 0 going to the m, which is the edge number, we read the edges one by one, so 0, 1. So this means if a graph in our heads looks like this, then in file we would have 0, 1, 0 for this edge, 0, 3 for that edge, 1, 2 for that edge. This is the file that we read from. This is the .in file, okay? The file that ends with .in. So we would have this in our edge array. So we would mark 0, 0 as 0, 0, 1 as 1. So this would mean, the 0th edge, this would go for the 0th edge. And this would be the first vertex of that 0th edge and the second vertex. So for the first edge, this would be the first vertex, second vertex. For the second edge, this would be the first vertex and second vertex. So as I said again, let me say again, this is not important for you to understand, but of course it helps to understand the general thing and feel good about yourself. Feel confident. So next thing, they initialize a graph that they give n, m, and the edge array as parameters. So there's the graph object here, graph class, that we will look at it more deeply. So then they call the initialize function. Okay, where's our initialize function? It's here, it's for us to implement, it's completely empty. Cool. So then they read the queries. If the type of the query is 1, then they call hasCycle. If it's 2, they call hasCycleWithoutNodeZero. If it's 3, they call isSameSet. If it's 4, they call getShortestPath. Okay, so we understood our main function. Now, let's go on with the graph. So this is a class that they create to represent our graph. In each question, this may be different. Okay, but it doesn't matter, because what matters is that you understand what the specific type of implementation is in every single question that you come across. You can practice this in CodeExpert, but if you have the idea in mind, idea of how to solve the question, this shouldn't be hard because they actually provide you the comments like this, such that you can easily implement your idea trusting these comments. So as I said, in fact, you don't need to understand all this. You don't need to understand this. The only thing that you have to look for will be the comments. So N is nodes, M is edges, N is nodes, M is edges, and so on. So if you understand the comments, you're basically safe. But as I said, we will be looking to the code anyways, just for completeness. So again, this is a graph object. Private integer n gives the number of nodes. Private integer m is the number of edges. These are the attributes. Private int degree array is the degree of vertex I. Edges are the endpoint of the jth edge of vertex I. Okay. And visited, whether node, they give a visited array as well to show whether node I has been visited or not for our convenience. Right. So they read n, m from the parameters that they provide here. Then they initialize the degree array and the edges array and the visited array. After that, they just read the edges from the edge array and then copy them to degree and to edges. Right, they just convert what we've read here in main function to a graph object instance, such that we can use it while we're implementing our answers. All right. Then there's an initialize method here also. Watch out for the comments. Note that we provide a method DFS which you might find useful. You're also free to modify the DFS method. Okay, here, surprisingly, they actually give the DFS method, but we will be using our own. If you want to use a queue, the following code declares one: queue integer, queue new linked list integer. This is not exactly my style because I think that people might mix things up like this. So I just use a normal linked list with add first, remove last, so that we explicitly see what we're doing. However, this is also free to use. You can obviously do it like this. This is just my style because I think it's more easy to understand and it's harder to mix things up. After that, finally, we have our queries: hasCycle, hasCycleWithoutNodeZero, isSameSet, getShortestPath, and the DFS help method that they provided. All right. So let's move on with actually answering the questions on paper, like actually having the ideas about the questions. So, hasCycle, return 1 if the graph has a cycle and 0 otherwise. So, we know that our graph is connected. So my question for you would be, what is the smallest thing that we have that is connected as a graph? What is the smallest graph that we have that is connected? I'm not talking about number of nodes, I'm talking about number of edges. Okay, so let me answer. As I said 100 times in my exercise session, the smallest thing that we have that is still connected is a tree. Okay, so if it has one more edge, then it will no longer be a tree because it would have a cycle. All right, so this is the idea that we are going to use. And what holds for a graph that is a tree? A graph that is a tree has n minus 1 number of edges. So if in a graph the number of edges is equal to n minus 1, then that graph is a tree, if it's connected though. So that's why we use this idea of connectivity all the time. So if the graph is connected, plus it has a number of n minus 1 edges, then it's a tree and it has no cycle. However, if its number of edges is bigger than n minus 1, then our graph has a cycle. So this is the exact same thing that we are going to use to implement. So let's implement. Alright, so here we have our hasCycle function. Weirdly, there's no dn.md file in this question example, but you can find it here. Just FYI, because I had a hard time to actually find the question before when I was you. So just FYI. Again, so we already have our number of nodes and number of edges. And to implement our idea, again, we need to return 1 if the graph has a cycle and 0 otherwise. So if m is bigger than n minus 1, then we have a cycle and we don't otherwise. So let's quickly check if we have our points. There you go, we have our first 4 points. All right. Now, next question. hasCycle without node 0. Suppose that node 0 is removed from the graph, return 1 if the resulting graph has a cycle and 0 otherwise. Okay, so what happens, again, if we remove node 0, we had this as a graph. So we had 3 connected components. Alright, so again, if a subgraph is connected, right? What is the smallest thing that it can be without having a cycle? It can be a tree, okay? So no cycle is the case when each connected component is a tree. So each set needs to be a tree. So for this example, m of set 1 needs to be equal to the number of nodes in set 1 minus 1, and m of set 2 needs to be equal to number of nodes in S2 minus 1, because again, this is the property of a tree, okay? So m of S3 needs to be equal to number of nodes in S3 minus 1. So here I'm noting down the notation. M of S1 means number of nodes in set 1. Okay. So you can realize one thing to have a quicker answer. So if you sum these things up, this would give the number of edges minus number of edges which we removed here, which is the degree of 0. Okay, and this thing here actually gives number of, wait, let me pick a different color. This thing gives number of nodes, okay, minus 1 because we removed 0, and this thing here is actually minus number of sets. Okay, so we actually need the number of sets. So this is a thing that we need to implement. Okay. So if m minus degree of 0 is equal to that, then all of the connected components are a tree and there are no cycles. This is the smallest case that you can have without cycles. This is the largest thing that you can have without cycles. It's the same thing because the graph is connected. It's a tree. At least it's a tree. So then if m minus degree of 0 is actually bigger than n minus 1 minus number of sets, then this graph has a cycle. All right, this is the idea. Okay, so how do we actually implement this? How do we find m minus degree of 0? And how do we find n minus 1 minus number of sets? Okay, so degree of 0 is easy because we already have it. N is easy because we already have it. M is also easy because we have it. The thing that we have to find is the number of sets. Okay. How do we find that? What we actually need to find in this example is we need to find the number of connected components, this, and this, after node 0 is removed from the G, which means node 0 and all the edges that contains it. Okay. So how do we find the number of connected components? We use DFS. But let's do the DFS starting from the endpoints of the edges that go from 0. Okay. If we do this and count the number of actual DFS main function is called, then we would have our set number. Cool. So let's remember how our things are implemented. Here, so we have degree and we have edges ij. So edges ij means the endpoint of the jth edge of vertex I. Okay, so we can just say edges 0, 0, 0, 1, 0, 2, and obtain every edge that contains 0. That's cool. And we have a helper visited array. Okay. And we also had a helper DFS function, which I will just quickly copy here, that we can use. So our DFS subroutine is already implemented. The thing that we have to do is the following. We loop through the endpoints of the edges of vertex 0. We do this by starting I from 0 and increasing its degree of 0 times, which is the number of 0 that 0 has. And let's use the visited array. So if visited edges that starts from 0 and goes to I, like the I, not goes to I, sorry, the edges that starts from node 0, we access this by edge 0, and I is for the 0th edge that starts from 0, for first edge that starts from 0, for second edge that starts from 0, okay? You can find this out from the comments. So, then, if it's still not visited, then call the DFS starting from that vertex. Then DFS visits that vertex, and for every edge that starts from that vertex, if it's not visited, it's called the DFS again. So we call this once here, and then, for example, we call this for 2, and then the rest is the 6, the 5, the 3 is handled with this DFS function, DFS subroutine here. So we need to keep track of the set number. And set number is actually an attribute that we want to access everywhere. So what we can do is, just like the degree, edges, visited, and M here, we can actually define an attribute for graph and make it public. Then we can use that set number and increase that set number whenever we find a new edge. So the thing that we did here is, for example, we are at 0. So for degree of 0, for every edge of 0, the first edge, let's say, is 1. So we increase the set number and call DFS from 1. Then everything is visited here. Then the second one is, let's say, 2. We start the DFS and visit everything. Okay. And then increase the set number to 2. Then 3 is already visited. We call for 4. We start the DFS. And DFS subroutine handles everything. And then our set number would be 3 by then. So 2 things that I forgot. First thing, we also need to initialize our set number to 0 here, because this is how it goes. Let me go like this to show that this is our thing. And we increase the set number. And the last thing that I forgot about is for the DFS subroutine to not come back to 0 and visit it and then go on like this and go on like this again, we need to initially say that we already visited 0. Okay. With this function, we actually find the set number. So now our sub-question needs to be easy. So again, just like this, what we were supposed to say. Okay, so if m minus the degree of 0 is bigger than n minus 1 minus number of sets, then return 1, else return 0. Cool. Let's test. Oh god, we have an error. This is a boolean and I said that it's an integer. So if it's false, there you go. There you go, we have our 4 points. So we're done with sub-question 2 as well. So next question. Given 2 nodes, x and y, return 1 if they're in the same set and 0 otherwise. So here, we are also going to use DFS, but we no longer only need the number of sets, but we also need the set ID for each vertex. That's the idea. So to every vertex, we assign a set ID. And how can we do this? We can do this by, in the initial function, in the initialize function, whenever we call a DFS, we actually need to assign the set number to that vertex. How can we do this? We can have an array of set ID of length n, and to each vertex we can assign a set ID. So here in our example, the set ID of vertex 0 could be 0, 1 could have 1, 2 could have 2, but the rest would also have 2, and 4 would have 3, and 7 would have 3 as well. So that's the thing that we need to achieve. So how can we achieve this? We need to modify our DFS. So how to implement this? First things first, we need an array that holds the set ID for every vertex. So for this, we first, let's say, we say that it's an attribute of a graph, and we also initialize it here. So set ID is an integer array of n. Okay. So here we're going to hold the set ID for each vertex. So I'm going to implement this here as well. So of course set ID of 0 will be 0. Okay. And then for whenever we call this DFS subroutine again, we want to have that new set number as a set number ID for that vertex. So whenever we achieve a new vertex that we didn't see before, we increase our set number from 0 to 1, for example, here, and then we assign 1, the set ID of 1. Then when the DFS subroutine finishes, and then we, let's say, call here again, then we assign the set, we increase the set number to 2, and then we assign that as an ID to node 2. Cool. But what we need to also do is to assign that 2 to every single following vertex that we have in that DFS subroutine call. So here we also need to do some things. Okay, so first thing, I'm going to take this out and call it current, because I don't want to think about it every single time. Okay, so that is the current vertex that we achieved from start vertex X. So if we achieved current from our start vertex X, so we called DFS here for that X. So we called DFS for 2, then we achieved 6 as current, for example. If we achieved 6, if we reached 6, that the set number, the key idea here is that the set number of the thing that we achieved, we reached needs to be equal to set ID of the thing that we come. So set ID of the current vertex needs to be the same as set ID of X. So we assign that same set ID to the current vertex that we reached from the previous one, X. Cool. Now we have the set ID for each vertex. And now we're done. So if it's the same set, if set ID of X is equal to set ID of Y, we return, there hasn't been a single time where I wrote return nicely, we return 1, and else we return 0. So let's test it, moment of truth. Oh God, I have an error again. I wrote set ID somewhere wrongly. Where? Here. Oh God, no. There we go. There we go. We have our 8 points. So, our next question. Get shortest path. Given two nodes x and y that are in different sets, return the shortest path distance between them. Okay, so first, let me erase this. First thing to realize here is that our nodes are now in different sets. So it can be this, wait, let me pick a color. It can be node 1 and node 3. It can be node 4 and node 2, but what it can't be is it cannot be node 2 and node 6. Okay? So the key thing to realize it, however you pick your nodes, it needs to go through node 0. So if you pick it like this, it was supposed to go from node 0. If you pick it like this, it goes from node 0. If you pick it like this, it again goes from node 0. If you pick it like this, it goes like this. So whatever. Okay? So the key idea here is that we find the distances to 0 for x and y. Okay, so distance to 0 x, distance to 0 y, and we add those two together, and the result that we have will be the shortest path distance. How and why? Because everything goes through node 0, and for example, if the shortest path of node 2 is 1, that goes to node 0, and then from 7 it's 2, then we have 2 plus 1 is equal to 3, which is the shortest distance between 2 and 7. That's the exact idea. Okay, so let's implement. So just like the set ID array, we need to have a distance array for distances to node 0. So we need to mark the distances to node 0. That's why we declare a distance array for distances to from node 0, and then we initialize it just like we did for set ID, and then we use this below. So this was our DFS. Now we're gonna do our BFS. And first thing to do, we used our visited array once. Unless you don't want to, create another visited array, you can also do that. But what I'm going to do will be that I'm just going to loop through that visited array and then assign each index to pulse again. Then we're going to need a data structure for our BFS, which will be a queue. I will use a linked list to implement our queue because it's just more obvious what you add first or remove as just like our BFS. So that's why I'm going to use this, but it's just purely a matter of style. Which one you prefer, doesn't matter. Which one is easier for you, you use that. Okay, so So we say we first add our node 0 because that is actually the starting node. We compute the distances to each node from node 0. That's why we add it first. And we also say that the distance from node 0 to itself is actually 0 because you don't have to move anywhere. So after that, we do the following. While RQ is not empty, we remove the first element from the queue, and then for every edge that goes from that element, if the node that we achieve through that edge is not visited, then we visit that edge, not that edge, we visit that node, then we say that distance to that node is equal to distance to our current node plus 1, because we just use that edge to achieve that node, okay? And then we add our newly discovered node to the end of our queue. So that is our BFS completely. Okay, whenever you have a BFS question, you use this exact same implementation, and whenever you have a DFS function, you use this one and that one as a base. So you change and modify one or two things, but it's basically the same. So learn these. Okay, so learn these. Really do learn these for your CodeExpert graph part. So then we use this to have the shortest paths from x to y, which is easily distance from node 0 to x and distance from node 0 to y. Let's check. Okay, it compiles, and let's check. Alright, best moment ever, the best thing to see at the end of a CodeExpert exam, right? So best moment for me, best moment for you, and we're done with our graph part. Any questions that you guys have are really welcome. So feel free to drop some comments or actually message me. I will also publish my DFS and BFS implementation and the actual code for this graph sets task. But most important thing is not to memorize this DFS and BFS functions by heart. Most important thing is to know the idea, because they can change how they represent the graph. Okay, but you know how to do a BFS. The only thing that will change is this edges current I thing here. Or you don't go by degree, you go by length of the adjacency list, or whatever you have on that specific graph implementation. Okay? So feel confident about what BFS is and how to implement it, what DFS is and how to implement it, and where to use them. Okay? That's how we achieve this really nice green bar in an exam. Okay. See you in the DP task video. Bye-bye.